Good morning, everyone, and welcome to this live session. So I'm delighted to welcome you all to this live and practical session on developing and deploying signal processing algorithms. My name is Abdurrahim Belaisawi, and I have been working for CS for a couple of years now, and my background is mainly in signal processing, control system, radar, and wireless systems. In today's webinar, I'll be talking about developing and deploying signal processing algorithms using MATLAB, Simulink, and other MathWorks tools. This topic can be broken down into the following outline. So we will see how we can import and work with signals in MATLAB, and then how to transform and analyze these signals using interactive tools and functions. Then we will move to the digital filters design and analysis. Most of the time we'll be doing that using apps and interactive tools. And then we will do what we call streaming signal processing systems. And eventually we want to deploy these DSP algorithms. So we will learn how to share them as apps, how to generate C or C++ source code from DSP algorithms from MATLAB and Simulink. And then we will see how we can generate for a target hardware, okay? And after that, we'll see a small introduction into how to generate CUDA code and HDL code. I would like to begin this session with a user story that encapsulates the essence of our topic, which is signal processing algorithms development and deployment. So this is about a startup called Yubi. So they created a software that can be used to track a voice, or what we call DNA, in a crowded environment and separate a voice of interest from the background noise. And these include other voices. So this approach, they used the approach which is based on MATLAB tools, and that includes signal processing and AI tools to improve the overall sound quality and speech command accuracy for far field application and speaker identification platforms. So basically the approach is like, it's called 3-in-1. So they used three main aspects and they used one environment, which is MATLAB. So with MATLAB, they built an app or application that combines signal processing, AI, and studio broadcast technology, which required a special development environment, which was MATLAB in this case from MathWorks. So I have attached the link here. So when we share with you these slides, you can learn more about this interesting user story and see how that can be applied to your application as well. Before even we develop these signal processing algorithms, we want to get these signals that we will use to test our algorithms. So to access data in MATLAB, there are different ways and different formats that are supported. And this can be done from many locations. So for general file formats, that can be an Excel file or MP3 or MP4. So we have many functions and apps that allow you to do that. The same for the local and cloud storage. You can connect your MATLAB and Simulink to the cloud and import data from there. The same for the databases and data platforms, and including MySQL, Databricks, and so on and so forth. And for big data formats like packets, you can still connect your MATLAB to such a platform and get your big data and analyze it using the convenient functions inside MATLAB. For advanced file formats such as MDF files or what we call industry specific. You can also connect your MATLAB and get data from sensors through some data acquisition devices. And this doesn't mean we cannot get climate and scientific data. So this kind of data is mainly stored in what we call HD5 HDF5 files, or any other one such as NETS, CDF. In this case, you need to keep in mind that you might require some support packages or toolboxes to import your data from different formats and locations. Now we have this data that we got from a location in a specific format. We want to analyze it interactively without writing a single line of code. We can use what we call apps. So these are pre-defined or pre-built apps inside MATLAB, such as import data and import tool. So you can import signals from files such as text, spreadsheet, and so on and so forth to MATLAB without writing code, as I mentioned. And then for plotting, and this is mainly in time and frequency domain, you can create a plot using a live task. This live task allows you to interactively create and explore visualization. And you have hundreds of plotting functions that you can also select from and plot your signals in time or in time and frequency domain. Now you want to analyze this data that you imported to MATLAB. We have an app called Signal Analyzer app, which is an interactive tool for visualizing, measuring, analyzing, and comparing signals in time domain, in frequency domain, and in time and frequency domain. And what you see here is actually the app, which is called Signal Analyzer, and it allows you to do many things, and it's all interactive. Another app that allows you to do what we call wavelet analysis is Wavelet Signal Analyzer. This app enables visualization, analysis, and compression of 1D signals using decimated and non-decimated discrete wavelet and wavelet packets. And you can use it for filtering and for compression, and then the workflow or the last step of the workflow is to generate a script or to export the processed signal to the MATLAB workspace. We will see these two apps. We will open them and do some activities with them, showing you how they work. And there are many other interactive tools, apps and live tasks. So if you are doing some signal analysis for AI application, or you want to label your signals, you can use what we call signal labeler. For wavelet apps, there are many other wavelet apps, such as Wavelet Signal Denoiser. And we have also Signal Multi-Resolution Analyzer and Wavelet Time Frequency Analyzer. These are some few apps that I added to my presentation. Please keep in mind that there are many other apps inside different toolboxes that you can explore yourself. And these apps will be always have examples and tutorials on how to use them. So before we move to the next part, I want to show you how you can use this Signal Analyzer app and Wavelet Signal Analyzer app inside MATLAB. For that, I have a small demo showing you how to find an interference in a signal. So this is my live script, and basically what I'm doing in this live script, I'm generating an interfered signal, which include a signal of interest and a chirp, okay? And then, so I'm generating this signal using the chirp function, okay? And I'm adding another signal here using the cosine function, and then converting to a timetable so that I have a signal and the time notion in that, okay? And then we will see how to use the signal analyzer app to analyze the signal in the frequency domain. Then in the frequency domain, using what we call persistence spectrum. And the last part of the workflow is to generate a MATLAB live script so that we can reuse it with our processing if we are doing any. Okay. So to start as I said, I'm going to use the Signal Analyzer app. This app can be found in the Apps tab, okay? And then you find Signal Processing and Communication group of apps, okay? And then you want to find the Signal Analyzer app. So this is the Signal Analyzer app. Just one click and then will open. Another way to start any app is to use the command window. So if I write Signal Analyzer, so I can start it this way as well. But I prefer like to use the apps tab, then you find the app there and you start it. Okay. Now I want to run these parts of my code so that I can get the signal that I'm going to analyze using the app. Okay. So as I said, I'm just generating a very small or a very short like signal, and I'm adding to it another one so that we have this interference aspects in it. Okay. Then I will go to the app. Okay, this is my app. And as you can see, the workspace browser, this is like the workspace of MATLAB is replicated here, and you can see already some variables. And the one of interest for me is this S, as I have my signal in that. So to start the analysis, all you need to do is to drag and drop from the workspace browser to the filter signals, and then you expand it and then you plot it. So this is the plot in the time domain, okay? Now I want to analyze this one. I want to do the analysis of my signal in frequency domain. That can be done by going to the display and then display tab, then find the spectrum, and then you click on spectrum and you will have the signal in the frequency domain. And what we are plotting here is the power spectrum. Okay. Next is to this plot doesn't tell me a lot about where my interference occurs. So I can do it in a different way so that I have better visibility where this interference is happening in time and frequency domain. To do that, you can upload the spectrogram. As you can see, I'm doing all that interactively. I'm not writing any code so far. Okay, and using also this, we can select this one as we don't need it anymore. Using the spectrogram, now we can see that there is another signal here, and this is our chirp, okay? And this is the cosine component that we added, okay? So it's still not that visible, this interference component. To better visualize it, I can try to find it using the persistent spectrum. And then I will go ahead and select this. So now doing it this way, I can see this is my two components in the signal that I'm analyzing. So with persistence spectrum, I have better clarity where my interference is happening. So based on that, I can maybe go ahead and design a filter to eliminate these components that I'm interested in. I'm not interested in. Okay. And then you want to zoom more on this. You can go to the parameters and change the parameters for the persistent spectrum by changing, for example, the mean, the max. This is for the power limits, or you can also play with the leakage this way. And then you will have the plotting updated. Okay. And for the measurement, if you want to do some measurement, I don't see an advantage of doing here or finding peaks because we don't have peaks here. So we are interested more in the analysis in time frequency domain. So last step in the workflow is to generate a script. Okay, I want to generate a script for the persistent spectrum, and that can be done easily. And here we go. We have ended up with this very nice script that can be used for automation, as I said, or even like you can create a function out of these and then generate the code for and deploy. Okay, so this is for a signal analyzer, the same workflow for any other app. So I'll try to show you the Wavelet analyzer app quickly. This is Wavelet signal analyzer. So as I mentioned in the slides, we use it mainly to denoise or compress signals. I'm going to try to denoise ACG signal in this case. I have it in the workspace. If you want to load it, you can use the load command and you're going to get it. So as you can see, we have the signal or the raw data here, and then we have what we call the composition coefficients. Okay. I skipped one part of the workflow, which is import. So it's important that you get your signal first to the scenarios, and then you start the denoising, or you start denoising or compressing your signal. Now I want to filter this, and I want to have what we call the ACG filtered for further processing. I can unselect these levels that I think that are not relevant or they don't contain any relevant information. I can filter them this way by just unselecting, and I will end up with this one, which looks like close to what we know about ACG signals. Then these can be we can also look at the coefficients, okay, or we can plot histogram, autocorrelation, energy by level, and so on and so forth. And eventually want to send to the workspace the analysis that we have done. So we can do it this way, and we will end up with another signal called this one, okay? So this one can be, or this signal can be easily now plotted and visualized so that you see how it looks like. Okay, so this was for analyzing signals. Now we want to move forward with filtering. So we want to talk about filtering. So signal processing for data analysis and systems, we usually have an input signal, and we want to process it using some algorithms, then an output, which is going to be a signal. What you see here, an ACG signal, this is a noisy one, and at the output we have the noised one, or a clean signal. And eventually you want to deploy this algorithms, not the output or the input. You want to deploy these algorithms to a target hardware that can be a microcontroller, a DSP, or any other hardware. And we want to have a product. So the main objective of any project is to have a product. At the end of the day, we want to have a product that we can maybe sell or hand to another team for further developments. In MATLAB and Simulink, this can be done in different ways. So if you are focusing on system design, so that can be done with the DSP system toolbox features, and then you can design a system with the algorithms. This include the modeling, design, development, simulation, and so on and so forth. If you are focusing on signal analysis, you can get your data that's our signals in this case to MATLAB and analyze them. What you see here is the primary features of DSP system toolbox is the system design and algorithm design. For the signal processing toolbox is data signal analysis, or what we call the offline analysis of signals. So digital filter design in MATLAB and Simulink is now very easy and straightforward. You don't need to write functions or you need to develop something from scratch. You have what we call live tasks. So we have a live task called design filter. It allows you to design filters and analyze them, and then use that filter to process or to filter out the unwanted information in your signal. And in Simulink as well, we have blocks that allow you to design filters, and you use the analysis tool for the analysis of your filter design. Basic filters can be performed or can be designed using the signal analyzer app, the one I just showed you, and you can design these basic filters like low pass, high pass, or band stop filters, and remove the trends, smooth a signal, resample a signal, or even you can use your custom function for filtering. Talking now more about the design filter live task, it allows you to pre-process and analyze signals in live scripts. Choose from most common FIR and IR design algorithms, visualize filters response and equivalent MATLAB code as you design. We will see how to use this app in a practical demonstration. So with the app, as I said, you can specify the pre-processing and analyze you can choose from FIR or IR design based on the response magnitude that you're gonna select, and then you can analyze it. You can analyze that filter in the app, in the live task itself, so you don't need to use other tools. And for more sophisticated design of filters and to design advanced filters such as multi-rate filters, you can use Filter Designer app. So it allows you to design, analyze, and implement filters for signal design and system analysis, for signal analysis and system design. Okay, and it has now another feature which was added recently. It's HDL workflow. You can generate an HDL right away from your filter design. To analyze filters, you can use a tool called FV tool. Okay, so it allows you to design filters, to analyze filters that you designed using any of these apps that I showed you before. So basically, what this function does the same thing as this function. So instead of writing functions and passing input arguments and spending time in that, you can focus on analyzing your filter using this app, which is FV tool. In Simulink, that can be done in MATLAB, and Simulink also can be done dynamically using this DSP dynamic filter, or you can use also the filter visualizer block inside Simulink. In addition to what I showed you, there are many other blocks inside Simulink that are inside the DSP system toolbox, allowing you to design multi-rate filters, implement the filters, design adaptive filters, design the filters using predefined blocks, and there are sources for many other filters. Now let's say we have designed a filter and we want to use it with a streamed signal from any of these platforms that I showed you in the beginning. So we are like, let's say we are getting a signal from a cloud, okay? We are doing an IoT application and we are getting a signal from the cloud, and then we want to stream the processing. We want to apply a filter on that signal. So with the streaming processing in MATLAB, you can do that. So because most of real signal processing application use streaming processing, which is a memory efficient technique for handling large amounts of data. For example, this is let's say the high level explanation of streaming processing in MATLAB. we need a stream source. This is the source of our signal. Then inside MATLAB, we have those algorithms for streaming the processing, and then we have the output. We can visualize it inside MATLAB as well. An example here is using what we call system objects. Okay, these are specialized MATLAB objects. Many toolboxes, include system objects. So with these system objects, you can stream processing. You can first connect to your device and then stream the signals inside MATLAB, and then process them and then display. So this is an example of processing an audio device, an audio signal coming from a device. We're reading it with this function, then we are filtering it, and so on and so forth, and we ended up with the filtered data. And this is how it looks like the code inside MATLAB, which is very, very short, a couple of commands, no more than that, to run the processing. So with DSP system toolbox, you can use algorithms that are already implemented using system objects. This will allow you to stream signal processing systems in MATLAB. Let's go to MATLAB and show you how to use these apps that I showed you for filtering, and then we will use a filter for we will stream that filter with the analysis as well. So I will go to this demo. Design, okay. So I'm doing actually the same. So, but this time I'm using DSP system objects, or I'm using the objects inside DSP system toolbox. So let me just clear the workspace. Okay. So I'm using this to generate a waveform. Okay. And later on, I will design a filter to keep only this frequency of interest, a component that I'm interested in. Okay. So I have 3 components, including the one of interest, and this is just the sample arrays in hertz. Okay. And after that, I'm using a plot function to plot or to visualize my signal that I'm going to process. So this is how it looks like. We can show it this way. This is my noisy signal that I want to filter to keep only the component of interest. Okay. Now using system objects as well, I want to analyze this signal. I want to analyze it in frequency domain or time frequency domain, and get some insights about what's going on with my signal before filtering it. So for that, I'm using the DSP, or I'm using the spectrum analyzer, which is inside DSP system toolbox, and the time scope to plot the signals in time domain. And these are nothing but input argument that you need to specify. So, sorry. So the number of input port means that the number of signals you want to analyze. Okay. I can run it this way, and I'm going to get the objects for the spectrum analyzer. I mean, I'm going to get the objects for my system, for my DSP system. Okay. Then now I want to design a filter. Okay. So this filter is going to be the DSP algorithm that I'm going to use to filter out the unwanted components from my signal. Okay. So to do that, I'm going to use this live task. So you want to add a new live task to your script. You can go to the live editor, then find task, and then find the one you are interested in or you want to use with your filter, with your analysis or filtering. So in this case, I'm interested in signal processing application, means that it need to be here. And then I can select the design filter, which will add this live task to my live scripts. Because I already have it, I'm not going to do that, but this is how you need to do it. Okay. So once you have the live tasks in your live scripts, you can design the filters quickly and by selecting just in an interactive way, selecting from the filter response. Then you need to specify the order in this case, I want it to be the minimum because I want to implement it maybe later. So I want the order to be the minimum. And these are the specification, or the most important parts of the filter design, is to specify the frequency parameters. How accurate is your filter? This is based on the stop band, because we selected a band pass filter in this case. That's why we need to specify all of these parameters for the frequency. So we have two. We have the stop band frequency and the pass band, and so on and so forth. And for the magnitude parameter, you also need to specify the attenuation for the stop band and the for stop band 1 and stop band 2. More settings can be defined or modified based on what you are looking for. So you can specify the algorithm for the parameters, and I'm going to use this Chibi here. So you can select any other one based on what you're trying to achieve. Okay. And match exactly, I'm specifying this to be pass band, and then I'm doing I want to see the response, so I need to select which analysis method I want to use, or which analysis approach. I'm okay with magnitude and phase. This is what I want to see. So the live script has this small button here that we can use to run. And once we run it, we're going to get the response. This is how the magnitude response and the phase response look like. And as you can see, it's a band pass filter. Okay. Now I want to use this filter to remove these components, these two, okay, and keep only the one of interest. It's called F, means that the frequency or the components of interest. Okay. So one more thing that I want to talk about here is that the name of the filter design, or the design of your filter, this can be found in the workspace after you run your live task. So and you can still change the name if you want to change it. This is the name of my filter. Okay. What I'm doing here, I'm streaming the filtering and the analysis as well. So I'm streaming the filtering using the filter function, and then passing the filter that I designed and the noise signal. So I'm using this function, and the input arguments are first the filter, and then the signal you want to the noise. Okay. But before that, I'm also calling this sig object, which is actually the object that will generate the signal for me. And then I'm calling the time scope, or the scope for time domain visualization, and the spectrum analyzer for the frequency analysis. So I will go ahead and run this. Okay, seems like I have a small issue here. I can resolve it easily. Okay, I need to release my system object before, and this is what we're gonna get. So this is the time domain visualization, and this is the frequency analysis. As you can see, I have only one in the filtered signal, which is in blue. I have only one component in my filtered signal. Okay, so this is how you can design a filter, or let's start it from the beginning. This is how you can generate a signal, and then design the spectrum analyzer and the filters, and then stream everything. This is very interesting, and you can't replace these generated signals, these synthetic signals that are generated, with your real world signal, and then stream them the same way I have done. The same filter can be designed using, as I said, the filter designer app. Filter designer app. So this will allow you to design and maybe deploy from there to the HDL, or you can also export to Simulink if you are interested in having a block for your filter in Simulink. So this is the filter designer app, and you don't need to start any or import anything from MATLAB workspace. You have everything here. And you can also import a session that you worked on before, okay? And then after you are done with the specifying the response type and the filter order, the frequency specification, and so on and so forth. Basically, these are the same as we did for the filter design live task. And once you are done, you can go ahead and click this design filter. Okay. Let me just show you quickly how you can do that. So I'm designing a high pass filter, and it's an FIR, and then the minimum order, and the density factor is 20, and these are the specification for my filter, and for the frequency, and this for the magnitude, and this is how you can design it quickly. Okay. So this filter can be analyzed further with looking at the response for the magnitude and for the phase, or you can even show the parameters that, or I mean the filter information. You can also analyze in different way by looking at the coefficients. These are my filter coefficient, the B and A coefficients, and yeah. So there are many other things you can do with this app. And it requires at least 1 hour to show all the features. I mean to say, this has a lot of advantages, and did mention that you can design multi-rate filters right away from the same app. So if you are interested in an in-depth session about filtering, we can also organize something about that. So this is for the filtering and filtering designer analysis inside MATLAB. Now, want to deploy what we designed. To deploy algorithms, and in this case, we are talking about signal processing algorithm. There are different ways. You want to generate an app from MATLAB that can be quickly done with MATLAB compilers. Okay, that can be MATLAB compiler and MATLAB compiler SDK, and the output in this case is going to be an executable, a MATLAB web app, or a Docker container, and the Excel add-in, Spark, or you can also deploy to an enterprise system using the MATLAB compiler SDK. So the files or the generated file is going to be microservice, or a DLL, or C++, or even a Python package, or a DLL shared library. Okay. And when it comes to generating the source code or a code for a target hardware, that can be done using decoders, and it can be done for MATLAB and Simulink programs. So you have a code in MATLAB, let's say an algorithm, a signal processing algorithms that you implemented using MATLAB, and you validated it and it's working properly. Then you want to generate a C++ code for a DSP or for a microcontroller from any vendor, and then you can use decoders. And in this case, you want to generate for a specific hardware, then you need to use embedded coder, or you can also generate an HDL or PLC coder, or if you are doing some signal processing and deep learning, then maybe the choice here is to generate a CUDA code. We'll look at some of these workflows in detail in the upcoming slides and demos. Okay. Let's talk about first sharing DSP algorithms as apps. So with MATLAB App Designer, you can build a modern graphical user interface with an enhanced design environment, expanded UI component, and also improved code and coding tools. These are the features of MATLAB App Designer that we will look at in a moment. Okay. So you will end up with something like this, a graphical user interface that you want now to take outside of MATLAB and share it with an end user that's going to be the operator or the going to be the end user for further analysis, maybe using that app you shared with him. So this app or this app that can be a standalone application or a web application or even an executable will require to install what we call MATLAB runtime. It's available online and you can download this for free and install it on your machine if you don't have MATLAB and you want to use this app. Okay, so this is the workflow. You do everything in MATLAB, then you compile it, and you end up with a standalone application. In this case, we are talking about standalone application, but it can be also a web application. Okay. Now let's go to MATLAB and see how we can do all this using MATLAB App Designer and MATLAB Compiler so that we can share our algorithm, which is in this case an audio player with emitter with other operators that they don't have access to MATLAB. So I'm going to go to this demo, share apps, and then I will open the app. So this will start MATLAB App Designer. If you want to start it, as I mentioned before, you can always write the command. If you know the command to start the app, you can do it this way. So if I run this, we'll start App Designer. But I want also to share with you that the extension for MATLAB apps is this ML app this way. So if you see this, it's a MATLAB application. All right, so now I have my app designer with this app that I designed before, and I want to talk quickly about the component library. These are the components that you will use to make or to create your graphical user interface for your app. So it's just drag and drop this way, okay? And then you end up with something like this. So there are components or there are blocks components for text, for let's say numeric values, and also for tables. If you want to display your data in a table, you can use tables. And we have containers as well. So this will allow you to organize and design a nice looking or a good app that you can later on compile. Okay. And for Simulink as well, we have some instrumentation blocks that allow you to get or to involve these aspects of changing a value of a signal, then showing that on a plot or something. So you have these blocks, and for aerospace, we have something like that as well, and so on and so forth. Okay. So for my app, I use this UI access, and then I use this text, use this for text, and I have a button here. So this I'm going to use to browse and get the file I want to process, and then I have this. This is also a UI access. I'm going to use it for the meter level so that we can see the level of or the amplitude of our signals in decibel. Okay, so this is actually nothing but the design view. So we want to program this app. This can be done with what we call the callback. So I can go ahead and create a callback for my for this function this way, or I can do it for the other ones, and then it will be in the code. So this is my code, and this is for the components that I have here. If I run this, I will end up with my app. Okay, so this is my app. I can click here, and it will start. Okay. Now I want to compile this so that I can share it with others. I can do this way. I want to generate just a standalone application. So you can do it this way, you add your information, then you decide to include or not the runtime. And then your package is this way, and then we will end up with a executable that you can share it with the users that don't have access to MATLAB. Okay. If you go to the yeah, so these are the files, and this is what you need to share with your colleagues that don't have access to MATLAB. So as you can see, this is an application. Okay. Next, we want to generate code, C or C++ code. This can be done using decoders and mainly MATLAB coder. This allows you to generate automatically code from MATLAB. Okay, and from Simulink, you need to use Simulink coder. For a target hardware, you need to use what we call embedded coder. So MATLAB to C++ made easy with MATLAB coder. So you can generate a C, C++, or a library, or even an executable. Or for acceleration, you can generate a max file. So the workflow starts with preparing, then preparing the code for code generation, testing it, make sure that it works in MATLAB, and then you generate. And this is a process, an iterative process. You can always go back to the preparation and then testing, and then you generate the code. Let me go to MATLAB and show you how you can generate C++ code from MATLAB. Okay, so I have here a filter that I designed using MATLAB. So as you can see, my design is nothing but some coefficients for my filter. And this is a function. The input is a signal that I want to filter. And in the other scripts, I have the information, or I have the script for testing, or what we call the test bench. I can run this, and I'm going to get this plot. This is the noisy one, and this is the filtered one. So let's say I'm done with testing my function, and it's working properly. Now I want to generate the code from. So that can be done using the coder. This is gonna start MATLAB Coder, which is an interactive app. It requires first to get the filter or to get the function you want to generate the code for. Then you decide about the entry function if you have any other. And for the numeric conversion, you can convert to fixed or convert to single precision. And then the project location, that's going to be the current folder where we are working. And then you click next, and you need to call this function or run it so that you get the definition of your, or the data type for your inputs. I'm going to get this file, which is the test bench, just for me to auto-define the input types instead of. Yes, please. Yes, please. All right. So I have auto-defined my input types, and it's double. As you can see, this is a C++ data type. It's called double, but it's also, I believe it's it's also MATLAB data types. Double. Now I can add more if I have some others. I can add them. Next is to check for runtime issues. That can be also done by quickly click on this check for issues. This will generate a trial code and build a max file and run the test file with the max. These are actually the steps that you need to perform if you want to test your code and its compatibility with code generation. So once I'm done, I'm going to click next, okay? And then I decide about the language I want to generate. I want to generate C++, and I want it to be functions only, not methods. I don't want to use the classes in this case, or the object-oriented programming. More settings can be done from here. You can change the memory settings. You can look at the speed and so on and so forth. This is something you can use to customize your generated code. Then next, and this is going to generate the code as C++ code for our filter. So the code was generated successfully, and we got a report as well. This is very important. document that you need to use, and it will allow you to trace or to look at your MATLAB code as well as the generated files, as you can see here. So these are the source file, these are the generated ones. The one with the same name as the function you are generating code for is what is the function that implements your MATLAB code. So this is the filter. As you can see here are the coefficients, and yeah, so we ended up with this C++ code that we can take now and deploy to incorporate it into an external code that can be a C++ code. Okay. So, and also there is a main function that you can use to run your generated code. So if you are familiar with C++, we have this main all the time. We have a main where we are calling our header and a file, and then you can validate your generated code outside in any other IDE, such as VS Code or any other development environment, any editor. Okay, so this is how you can generate the code from MATLAB. It's very straightforward. Only if you are interested in customization, you need to go into the settings and change whatever you are interested in. When it comes to Simulink, we can also generate code from Simulink. Okay, and this aligns very well with what we call the model-based design. So the model-based design allows you to model and simulate your system, test early and often, and then automatically generate the code. So we are going to use, let me look at the other part. The next thing is to generate a C or C++ code from a Simulink model. But before that, I want to highlight that you can also include your external code, something you developed in C or C++ using these blocks. You can incorporate it into your Simulink model, and later on you generate the code for the whole thing. Okay. So with embedded coder, you can generate C or C++ from models that represent a discrete time system. And this is the workflow that we're gonna explore in a moment. So we want to generate embedded C++ from a Simulink model. Let me go back to MATLAB and then go to deploy DSP and find this one. Again, this is a smoothing filter or a low pass filter that I want to generate the code for. I'm testing it, and then I'm going to use this one to generate the code. So remember that we want to generate the code for an embedded hardware. So we need to select the hardware we want to generate the code for and change the settings accordingly. So what this gonna do, it's gonna start Simulink and open this code that's this Simulink model that I'm going to generate the code from. So as you can see, it's a very basic filter. It's a low pass filter that I designed using only Simulink basic blocks, okay? And I can test it. So you can test it and see the input and the output signal, the noisy and the clean one, and then generate the code for. So to see that I added some viewers here, I can go to data inspector and quickly visualize the filtered and the noisy signals. Because they are discrete, that's why they look like this. So yeah, so in blue we have the filtered one, and then the other one is the noisy. So this is just for verifying the model before generating the code for. Now we want to generate the code for this filter. So that can be done by using the app embedded coder. So this app will allow us to generate the code for a target hardware. So first of all, you need to change this generic real time to what we call embedded real time, because we want to generate for hardware. And then you have a couple of features embedded into this embedded coder that you want to try. Okay, first of all, you want maybe to generate the embedded C code or C++ code or a shared library. I'm going to select C++, or let's generate C in this time, and then you have the quick start. This will allow you, or will show the workflow with the steps and the settings. This is very important. You need to change always the solver from any type to fixed step. And the solver that I'm going to use in this case is automatically found by Simulink, so it will not change this one. Then you want to go to code generation. So here you can still change the parameters or the settings, the language you want to generate, the system target, and the build process. So this will try to find which tool chain is installed and then generate the code based on that. And you have some advanced parameters that you want also to check if you are generating the code for this for something like very specific. You can go ahead and check these parameters. Okay. And for the hardware implementation, so because I'm using my laptop, now I got this one. If you are using any other hardware, you will be able to see that hardware. Okay. Next is to decide if you want to build or generate the code. So let's generate only the code. Okay. So this will generate a C code for my filter, and then we will have also a report. This report can be used, or the code viewed can be used to trace. This is the report. The same for MATLAB coder. We have a report that we can explore and use for inspection. And the code is allow you to trace between the generated code. If you go ahead and click on this, will take me to the code. This is the C code, and this is very helpful for tracing. Okay. So this is how you can generate a code for an embedded system or for embedded hardware. I generated it for my system because I don't have any other hardware connected to my laptop. So that's why I generated it for my operating system only. Okay. Going back to the slide, we want to discuss a bit this GPU coder. So you can generate CUDA code as I mentioned. The workflow is the same. You prepare, then you test, then you generate a CUDA code or a max file for acceleration. You have a Simulink model or a MATLAB code, then you use the GPU coder, and then you end up with a CUDA code that you can take and deploy to your GPU device. And for HDL, you can do it this way. You can also use MATLAB and Simulink for prototyping or for implementation and verification. Then you use HDL coder, and then you generate the VHDL code. And these are the different features of this HDL coder. Now let's look at an example and see how we can generate a deployable HDL code. I will go back to Simulink and then try to generate the code for the same filter that we saw before. Okay. Let me just close some of this, especially in Simulink. I think now I'm good. I can go ahead and yeah. So this is actually the same filter. The same filter, and I want to generate HDL code from. So the same workflow. I will try to find an app that allow me to generate the HDL code, and it's in this case it's HDL coder. So it will open this new tab. It's called HDL code, and it has some other features. Mainly this workflow advisor. It's very important to go through this one, as it allows you to check the compatibility of your Simulink blocks with code generation, with HDL code generation. And in that, you will have some tasks that you want to double check. So you can do that separately by running all. I mean, by running one by one, or by running all of them at once. Okay. So I'm going to skip this one as it takes a bit. So to check for the compatibility, and I'll go ahead and go to the settings. This is very important. You need to go to the settings and first change that to the block you want to generate for. I want to generate for the LFP only, then the target, and then the optimization. And you have many other parameters that you want to check and see if you need to select or unselect them. Okay. The next step is to generate the HDL code. So now the HDL coder is trying to generate the HDL code for my Simulink model, and I'm going to get everything here. So, okay, seems like there is something that I need to check. So I need to check this one and try again. Let's generate the HDL code now. Here we go. So I have this HDL code here. It's gonna have my HDL code, and they can use it for tracing and navigating between the code and the Simulink model. So if I click on that, and here we go, we have my entity, we have my architecture, and inside it we have some components. And as I said, I can use it to trace between the generated code and then the Simulink model. And so yeah, so I believe that's all. So for this quick demonstration, and then the key takeaways from this session: MATLAB and Simulink allows seamless signal access and streaming. With MATLAB and Simulink, experts or domain experts are doing fast prototyping of signal processing systems, the same UV did. So this startup I talked about in the beginning. And with MATLAB and Simulink coders and compilers, you can generate code and apps with single click, as we saw.